Hey everyone, in this video we're going to be taking a look at something called a higher order derivative. And basically what you can think about in this video is in the previous videos when we've calculated derivatives, you could say we did a first order derivative. In other words, we did a first derivative. However, in calculus, we often want to find a second derivative or in some cases even a third derivative. An instance where you'll see this, and in future videos we'll do a little bit more time to this, but we would call, in the future we'll see S of t that represents a position function. And if we were to take the derivative of that, call S prime of t, well that actually gives us what we're going to call V of t, which is the velocity function. And then if we were to take the derivative of that, so in other words the second derivative of S of t, which would correspond to the first derivative of V of t, that actually gives us what we call A of t, which is acceleration. So a good example of when we would want to take a second derivative is if we were given a position function and we were asked to find the acceleration function. Well, the first derivative would give us velocity. Take the derivative again, we get acceleration. And then we have a function in which we can find the acceleration of some given object at any point in time. The derivatives also tell us things about the slope of the function or the shape of the function, which we will again talk about in future videos. But for today, we're just going to focus on finding a second or a third derivative. Again, third derivatives aren't quite as useful, but you still need to know how to do them. And we'll look at a few different ways of representing this in terms of just notation. You'll also notice in these, on all of these, they're written with just negative exponents. So we're going to be using our power rules from the previous videos, and you can just leave them as negative exponents. Generally, when you do higher derivatives, they're not quite as picky on whether you rewrite them in simplest form. And also recall, if it's given with negative exponents, generally you can write your answer with negative exponents. And if a problem's not given with negative exponents, then you would generally not want to have negative exponents in your answer. So let's go ahead and get started. This question is asking us to find f double prime of x, meaning the second derivative. So all we're going to do is just take the derivative and then take the derivative again. So the first derivative of this function, f prime of x, using our power rule, we're going to do -4 times, and I'll write this one out, -1/4 times -4, because we bring it down, x to the -5th. Actually, write it down here. Sorry. A little more space. So we bring that -4 down in front. So it'll be -1/4 times -4. X to the, we subtract 1 from the power, so it'll be -5th power. That'll be our first term. Plus, we're going to bring the 6 down in front and multiply. So 2/3 times 6. X to the, subtract 1, so that would be 5th power. And then plus, and now we have 5/16 x. Well, we bring down the 1 power, multiply, and then the x actually just goes away. So the derivative of that is just 5/16. And obviously we'd want to simplify that a bit. So this would actually become just +1, -1/4 times -4, just +1, x to the -5th. And then 2/3 times 6 would give us 4. So +4 x to the 5th plus 5/16. So that's our first derivative. So now we want to go ahead and calculate the second derivative. So we just take this and then we compute the derivative from here. So f double prime of x, we need to bring the -5 down in front. So -5x to the -6th. An easy mistake on that is to say -4th. But again, we're always subtracting a power, so it gets even smaller. So -5x to the -5th. 5 times 4 gives us 20, so plus 20x to the 4th power. And then the derivative of a constant just goes away, so that 5/16 is completely gone. And this is what we're left with for our answer. Let's go ahead and type that in. Again, it's okay to use negative exponents on this particular problem set. If you wanted to do just a little self-check, Just make sure all of your exponents are 2 lower. So this was -4, and we ended up with -6. This was 6, and we ended up with 4. This was the first power, so it went to 0, and then it went away. So good little self-check. All right, let's look at a couple more. This one is just a slightly different notation, but it means exactly the same thing. So this is d squared y dx squared. This means a second derivative. So I guess the correct notation we would write this one would be dy dx would be our first derivative. So we're going to do -3 times -1/3. That becomes a positive 3/3, so that would just be 1. So 1x to the -4th because we subtract power. Next one, -2 times 1/6 would be -2/6, which would be -1/3. -1/3 x to the -3. Bring the 4 down, -4x to the third power. So that's our first derivative. Our second derivative, the notation we use here, just like it says up there, is d squared y dx squared. It's kind of, again, a weird notation, but that means the second derivative. Little square there, whoops. So then we just do it again. So bring in the -4x to the -5th power. This multiplies -1/3 times -3 would be +1, so plus 1x to the -4th. And this multiplies 3 times -4 is -12, x squared. And there we go. And we'll do maybe 1 or 2 more. So really, this isn't anything different than what we did on the previous video where we did power rule. It's just doing the power rule twice. That's all there is to it. Let me see if I can find a third derivative here. There we go. All right. So you can see this is d cubed y, or just d to the third y over dx to the third. So that means a third derivative. So let's go ahead and jump in. I'm just going to do it 3 times. So our first one, and we'll call this dy dx. That becomes 3 times 3/2 would be 9/2. Also remember, on all of these, this is going to be a non-calculator section, so you really just got to be good at your basic math skills. It does pay to know like just basic multiplying fractions and things like that, because the less time you spend on that, the more time you have to devote to the problems. So 9/2 x squared plus 5/3 x to the 4th. Now the derivative of the 3 is just going to go away now because the derivative of any constant is just 0, so it goes away. Plus 2/5 x to the first power. So that's our first derivative. Second derivative is d squared y dx squared. So 2 times 9/2, that's just going to be 9 because it'll be 18/2, which would be 9. 9x to the first power. Plus 4 times 5 would be 20/3 x to the third power. And 2/5 x just becomes 2/5. And then our third derivative, right over here, d cubed x over, d cubed y over dx cubed is going to be 9. The x just drops off, plus, that would be 60/3, which is just 20, x squared, and then the derivative of the constant just goes away. So all we're left with is 9 plus 20x squared.